right? So how do we confirm that? Actually, analytically, the way of confirming it is basically the same way as we used to derive our scheme on Monday through Taylor series analysis. But now here, you have to expand the Taylor series to more and more terms. So let's do that, okay? And in general, you don't actually know in advance how many terms you have to expand. So if you, let's say, expanding to 4 terms in Taylor series, and then you plug all the Taylor series into the numerical scheme, and you find that the result is exactly equal to what you want to approximate. You have no error. What does that mean? Too many terms? I don't need that many. If I find that my what I'm exactly equal, yeah, you have too many terms to derive the scheme, but you have too few terms to derive the error of the scheme. Okay, so if everything cancels exactly, that's great. I know the scheme is accurate, but I still don't know to what order the scheme is accurate. I have to find out the first term that doesn't agree to figure out what is the leading error term. Okay, so let's try that. And for this one, I mean, this is like the most popular finite difference scheme. So people already find out how many terms you have to expand. It turns out you have to expand all the way to the 4th order derivative. So let's do that. In general, you don't know that in advance. You have to try it. So if you expand the 4 terms, you find out everything cancels. Try one more term. Everything cancels. Try one more term. The more terms you add, you have to add for the first thing to not cancel. That means the higher order the scheme you have. So here, the 3 terms we have to expand is this, this, and this, right? 2wi, I mean actually minus 2wi is trivial. Minus 2wi is equal to, well, minus 2 times wi. Okay, so the reason I have to write out the trivial term is going to be obvious later on. wi plus 1 now is equal to wi, the value of w at I times delta x. Well, remember that's a shorthand for w at xi, which is I times delta x plus delta x. So using this for Taylor series expansion, we have more terms. We have a term that is proportional to dw dx at xi times delta x. We have a term that is a second derivative times half of delta x squared. We have now a third derivative times delta x cubed divided by 3 factorial, which is 6, right? We have 4th order derivative times delta x to the 4th divided by 4 factorial, which is 24, plus, let me just write O delta x 5th. Okay, and wi minus 1 is a shorthand for wxi minus delta x. Is expanded the same way, except all the delta x's are replaced by minus delta x. Second order derivative, I think I'm just going to skip all the derivatives. So this is minus delta x squared, which is the same as delta x squared, plus same thing, but minus delta x cubed over 6, plus same derivative, but now plus delta x 4th divided by the same 24, plus the same error term. Big O notation, delta x to the 5th. That means the big O notation contains term that is proportional to a constant times delta x to the 5th, plus potentially another thing that is a constant times delta x to the 6th, etc., etc. Right? Okay. Now we have to add these 3 terms together, and let's add vertically. Let's add vertically. So here, the first term, the 0th order term, goes to what? 0, right? Minus 2, 1, 1 gets cancelled. The second term, again, gets cancelled. Delta x minus delta x. This term is the first term that doesn't get cancelled, that actually produces the desired derivative. I mean, remember, everything is divided by delta x squared, right? So that's why we have the delta x squared here, is to cancel whatever that is added over here. So that is actually exactly delta x squared times the second order derivative we wanted to get. Okay, and we have plus, of course. And here, again, this cancels with this, right? So we have a 0 here. And it turns out the fourth order derivative is the first term we don't cancel. And the result is delta x to the fourth divided by 12. Okay? So that means the error we are having, let me denote as EI. Oh, actually, the usual notation is tau I. That's the truncation error. Stands for T, right? Because this is the error due to our truncating the Taylor series, right? So if you truncate the Taylor series over here, or if you truncate it over here, then there is no error, right? So basically this is error due to us truncating the Taylor series in this analysis. This is equal to, this is defined as the difference between the analytical derivative and the numerical derivative, the finite difference approximation. So basically in MATLAB, but that's the difference between the, oh, which one is which? Yeah, between the blue curve, which is analytical derivative, minus the red curve, which is the numerical derivative, right? So this is equal to, okay, so that basically means I'm going to take the entire black line, multiply it by minus 1 over delta x. Okay, and then add it with the second derivative. Okay, so what I have is basically the second order derivative. I just going to copy it, minus 0 plus 0. These are the two terms. Well, minus 1 over delta x squared, 0, 0, second derivative, plus again 0, and the fourth order derivative, delta x fourth over 12. So that's the truncation error. And we can see that this term cancels with this term, right? Because there is a delta x squared. The remaining part is only this term, actually minus fourth order derivative of w times delta x, what? Square, right? This square is the most important thing that comes out of this analysis. We have a fourth over here and a square over here. The resulting is something that is proportional to delta x squared, right? That's the primary purpose of this analysis, is to get that the leading term is proportional to delta x squared, the leading term in the approximation error. The remaining term that we wrote as O delta x fifth is also going to be divided by delta x squared, the result of which is O delta x cubed, right? So these are going to be small when delta x is small compared to this leading error term.